This is Gyroscopic Precession, Part 8. At the end of Part 7, we determined that we had 13,159 pounds per square inch of tensile and compressive stress in the propeller shaft. Each time it rotated a half a revolution, the stress was a result of the gyroscopic precession. Now we're going to look, well, because the propeller shaft was being bent back and forth, because the axis of the propeller shaft was changing direction, now we're going to look at the torsional stress, which will be shear along the outer edges, mostly, of the propeller shaft, that exists even when the propeller shaft is not changing direction, simply because the engine is turning the propeller. Okay, let's say the engine is producing 25 horsepower while the propeller is spinning 2100 revolutions per minute. Okay, here's what 1 horsepower is. Power, by definition, is work divided by the time that it takes to do that work. Well, 1 horsepower is 33,000 foot-pounds per minute. If you lift 33,000 pounds 1 foot, and it takes you a minute to do it, you're producing 1 horsepower. If you lift 1 pound 33,000 feet in a minute, you're doing 1 horsepower, producing 1 horsepower. So 25 horsepower will be 25 times all that, which is 825,000 foot-pounds per minute. Okay, our propeller is turning 2100 revolutions per minute. Well, there are 2 pi radians in a revolution, so that times that will give us 13,195 radians per minute. That's our rotational angular velocity. Okay, so the torque in the propeller shaft, due to the driving force of the engine, is the torque in the propeller shaft is 63 foot-pounds of torque. We get that by dividing the work, 825,000 foot-pounds per minute, by the number of radians per minute. So it gives us that. For a more in-depth explanation of this, go to the calculus lesson, part 9. The first 2 minutes explains it a little better. Okay, here's the formula that relates shaft torque and stress in the shaft. Okay, that was from our integral calculus lesson. You can see that formula again also in calculus part 9. Okay, so 2 divided by 4, same as 1 divided by 2, so this equation is the same as this one. Okay, if the torque is 63 foot-pounds, then it's 63 times 12, which is 756 inch-pounds. Okay, so 756 inch-pounds is the torque, which is equal to all that, which is equal to that, so we just stick that right here. Okay, we want to find the stress at the outside part of the propeller shaft, the part along there. If this were the propeller shaft, the stress isn't near as much in the middle of the shaft. And we want to find the stress at the outside, the maximum stress, this S max. So we just multiply both sides of the equation by that, or divide both sides of the equation by that. Okay, so S max is going to equal that divided by that. So there we have it. S max equals that, 756 inch-pounds, divided by pi r cubed over 2, divided by pi r cubed over 2. The diameter of the propeller shaft of the steel stork is 3/4 of an inch, so its radius is half that, or 3/8 of an inch, and 3/8 in decimal form is 0.375. So what we have is the stress in the propeller shaft is that times that over pi times that to the third power. Punch that all into your calculator and you'll see that the stress is 9,127 pounds per square inch. So we have 13,159 psi of alternating tensile and compressive stress in the shaft, which is due to the gyroscopic torque that the propeller puts on the shaft. We also have 9,127 psi of shear stress due to the engine driving the propeller. So if 15,000 psi is the maximum stress allowed in only one direction with no other stress in any other direction, can we allow 13,159 psi in one dimension and 9,127 psi in a perpendicular dimension? Okay, there's what we have divided by the max that you can have without having any other stress. We square it, add it to the other stress in the other direction, divided by the maximum amount that we could have in that other direction if we had none in this direction. Square that, add them together, we get 1.14, which is a little bit too much. This has to be 1 or less. This exceeds our allowable resultant stress. So the pilot of the steel stork better limit any changes of propeller shaft axis to no more than 50 degrees per second. We determine this stress based on angular velocity change, or the change in the axis. Remember, when we're at a full power stall and we drop 1 radian per second, that's based on 1 radian per second. So if we only change the axis 50 degrees per second, 1 radian is 57 degrees. If we only change it 50 degrees per second, we'll be within the parameters. So that's how the steel stork better be flown if we don't want to exceed the allowable stress limits on the propeller shaft.